Good morning, all. Am I audible? Are you able to hear my voice? Yes. Are you able to hear my voice? Is the screen is visible? Okay. So once again, good morning, all. This is the video lecture on design and analysis of algorithms. We are discussing with module 5, that is backtracking. So in the yesterday thing, we have discussed about graph coloring and Hamilton cycles. So in today's class, we are going to discuss with a branch and bound. So under branch and bound, you are going to have two concepts. So one is the assignment problem, the other one is the traveling salesman problem. So we have already seen the assignment problem here. So now you come for the next concept, that is traveling salesman problem. So what you come across the traveling salesman problem. So we will be able to apply the branch and bound technique to instances of the traveling salesman problem if we come up with a reasonable lower bound on two lengths. So what is the general concept of traveling salesman problem? So one person should travel starting with the source and visit all the nearby cities and finish with a started pointing only. So start with the same city, travel to other cities and finish up with the same city. So that is the traveling salesman problem. So here you have to discuss with two things. So first concept is, so source vertex as well as destination vertex should be same. Okay, so both should be of same, and here has to visit all the nearby vertices such that you have to branch from one city to another city and bound within nearby cities. So bound to particular cities. So one very simpler lower bound. So lower bound you have to find. One very simpler lower bound can be obtained by finding the smallest element in the intercity distance and multiplying it by the number of cities. So obtained by finding the smaller element. So which is the smaller element you are having? So that is the nearby cities. For example, if you are in Tiptur, which is the nearby city, like you can think of Tumkur, or you can go for the Arsikere, like that. So finding the smallest element in the intercity distance matrix and multiplying it by number of cities n. But there is less obvious and more informative lower bound for instances with symmetric matrix D. So for each city I ranging from 1 less than or equal to I less than or equal to n, find Si. That is sum of distances from city I to two nearest cities. So find for each city you have to compute two things. So first is the find Si and second one is the compute S. So what is the find, how to find the Si? So sum with respect to some city. So sum of distances from city I to two nearest cities. So from one city to two nearest cities, what is the distance you are having? The sum of that will be the Si. So compute S. The sum of Si I equals 1 to n, divide the result by 2. So this is a branch and bound traveling salesman problem example. So you are starting with the sources A, and which is the destination, which is the last node you are having. So last node is B, second node B, third node C, fourth D, and finally E. So which is the last node you are having? It is E. So now you have to find the path from each and every vertex. So which is the nearby two cities, which is the distance you are having from A, you are having 1, 3, 5 and 8. So you have to go with all the, start with A. So starting with A, you can take it as first you are having 1, next is 3, next is 5, next is 8. So from A, there are 4 routes for B, for C, and for D and for E. So in that, which is the lesser one for A? So two nearby, you have to take it. A to C is 1, A to B is 3. So 1 plus 3 that we will be taking here. Okay. Now you come for the B part. So B part, which are the vertices? B to, here it is 3, here it is 7, here it is 6, here it is 9. So 3, 6, 7, 9. So in that, which is the smaller one? 3 and 6. So take 3 and 6 here. Come for C part. So C to A 1, C to B 5, C to D 4, C to E 2. So in that, which is the nearest one? 1, other one is 2. So that's why we have taken 1 plus 2. Next come for D. So D you are having, this one is going at 5, this one at 2, this one at 7, this one, this is 3, this is 4, this is 5, and this is 7. So in that, which is the two nearby you are having? So two nearby things are 3 and 4. So this is 3, this is 4, this is 5, 7. So in that, which is the two nearby? It is 3 and 4. That's why we have written it as 3 and 4. Finally come for E. So coming for E, you are having, so from E to C, the path is 2. From E to D, it is 3. So from E to A, it is 8. From E to B, it is 9. So in that, which is the two smaller cities you are having? It is E to C, you are having 2. E to D, you are having 3. So 2 plus 3. So everything you made by 2, divide by 2. So that will give you the lowest bound. Okay. Okay, to reduce, what is, how much is the lowest bound you are finding? 14. 14 is the lowest bound. So under that, to reduce the amount of the potential work, we take advantage of two observations. So to reduce the amount of potential work, we take advantages of two observations. First, without the loss of generality, we can consider only tours that start at A. Consider only the tours that will start at A. First, without the loss of generality. So now you have got the lower bound. How much is the lower bound? It is 14. To reduce the amount of the work, we take advantage of two observations. So first, without the loss, we consider only the tours that start at A. So start at A and end at A. As you all know, traveling salesman problem start at same location, finish at same location, but visiting all the other nodes. So that's one. So that's why you have taken, we consider the tours that start at A. So now you, secondly, because our graph is undirected, we can generate only the tours in which B is visited before C. Okay, so here you can see the tour. So it is from A to B, B to C, C to D, D to A. So we have taken, but you come for the remaining things. So B, C, D. So starting point will be A, ending point will be A. In between, what are the tours you can have? It is B, C, and D. So now you have the multiple permutations of combinations of these things. So if there are 3, so first you take BCD, next you take BDC. So just for B you are having CD and DC. For C, again you have, if C is there, you can have D, BD, the other one is DB. Next for D you are having BC as well as CB. So just you interchange that thing. Now you come for the length part. So coming for the length part, A to B. What is the length from A to B? It is 2. So length part from A to B is 2. From B to C. B to C is 8. From C to D it's 1. And D to A it's 7. So that is equal to 18. So now you come for the second path. A to B is 2. B to D is 3. And D to C is 1. And C to A is 5. So that is equal to 11. Next, A to C is 5. And C to B is 8. And B to D is 3 and 7. So that is equal to 23. So similarly, you start with A to C. A to C is 5. C to D is 1. D to B is 3. And here it is 2. That is equal to 11. That is optimal solution. So because when you go for all the path, you which is the smallest two distances you are getting. So one distance is A to B, B to D, D to C, and A. The other one is A to C, just the reverse of this one. So what you have written, you start from here, A to C, C to D, D to B, and B to A. So that is the two results what you are getting at as optimal. Okay, so in addition, after visiting n-1, that is 4 cities, a tour has no choice but to visit the remaining unvisited city and return to starting one. The state space tree tracing is shown in figure. So this is the state space tree, what we can see. So initially we all know how to find the lower bound. Lower bound for A is 1 and 3. Lower bound for B is 3 and 6. Lower bound for C is 1 and 2. And lower bound for D is 2 and 3. Lower bound for D is 3 and 4. Lower bound for E is 2 and 3. Everything by 2, that is equal to 14. So now you start at A. So initially at starting at A, lower bound is equal to 14. So now you have the combination for AB, AC, AD, and AE. So A is being combined with B, C, D, as well as E. So what is the lower bound you find from A to B? So if you are finding the lower bound from A to B, A to B, so you can take it as 14. Okay, so A to B, you are getting it as 14. Next, A to C, is there a, what is the thing you are getting? A to C. So A to C, there a path? Yes, B is not before C. Okay, so B is not before C. So next you go with a comma D. So this is the A comma D. You can take it as 16. So how you get this particular thing? A to D. So A to D have to go with things. So that is equal to 16. So LB is greater than or equal to 1 of node 11. So A to E, you're getting it as 19. So now you come for the three combinations, ABC, ABD, ABE. So its lower bound is given like this. So after three combination, now you go with the final one, ABCD, ABCE, ABDC, ABDE. So first tour, better tour, inferior tour, optimal tour. So out of all this, which is the optimal tour? L is equal to 16. So this is the optimal. So this is the optimal. So this is the final, you are getting the final thing what you are getting, the first tour, better tour, inferior, and optimal. So very optimal tour, it is L is equal to 16. So this one, it is very near to our lower bound. So we take this one as So this is the optimal tour what we are getting. So as we found the lower bound is equal to 14. Now next lower bound is you are getting it as 16. So that's why we tell this one as a optimal tour. So now you come for the next topic, that is 0 bar 1 knapsack problem. So knapsack problem. So how do you find the branch and bound solution as well as FIFO branch and bound solution? So you are getting this knapsack problem in a greedy method. So again in dynamic programming, again in greedy, dynamic programming and backtracking. So now we are applying the 0 bar 1 knapsack problem in the backtracking method. So branch and bound solution to 0 bar 1 knapsack problem. So problem definition. As you all know, so given n items of known weights Wi and values Vi, I ranging from 1, 2, 3 up to n, and the knapsack of capacity W, find the most valuable subset. So you will be finding the most valuable subset of items that fit in the knapsack. So that means we are having n items. So each item is of weights Wi with their respective values Vi, ranging from 1, 2, 3 up to n, and the knapsack of capacity W. Find the most valuable subset that fit in the knapsack. So that we are giving it as so summation. Most valuable subset that fit in the knapsack. So given as WIXI less than or equal to W. So this is the one thing, and PIXI is maximized where XI is equal to 0 or 1. So it is convenient to order the items of the given instance in descending order by their value to weight ratios. So that is given as Vi bar Wi greater than or equal to V2 bar W2 up to Vn bar Wn. So value bar weight of first item should be greater than or equal to value per weight of the second item, and it should be greater than so last item. So each node on the ith level, that is ranging from first to last, represent all the subsets that include a particular section. So how to compute the lower bound and upper bound? Okay, so till now we have gone with a lower bound as the mean value of the least value of each item. So now you come for the computing the upper bound. The simple way to compute the upper bound UB is to add to V the total value of items already selected, the product of remaining capacity of the knapsack W, and the best per unit payoff. So that is upper bound is been calculated as V plus W minus W, Vi plus 1 divided by Wi plus 1. So upper bound is equal to weight value of each item. So V plus W minus W Vi plus 1 by Wi plus 1. So consider this particular example, and we have to apply the branch and bound solution algorithm for this thing. So consider the following problem. Elements are already ordered in descending order of their weights to value ratio. So it's already been sorted in descending order. So as you all know, the first value should be greater than second value should be greater than third value should be greater than fourth value. So here they have given values as well as weights. So this is the computed value of us. So 40 by 4, it is equal to 10, 42 by 7 equal to 6, 25 by 5 is equal to 5, 12 by 3 is equal to 4. So knapsack capacity W is 10. So now we shall apply the branch and bound algorithm. So when branch and bound algorithm, so what is the total space you are having in this particular thing? So first you start with this one. So value weight is been assigned here. So initially W is equal to 0, V is equal to 0. What is the upper bound value you are having? So how to calculate the upper bound value? So take the entire thing of this. So 40 plus 42, 82, 82 plus 25 plus 12. So upper bound, it is greater than 100. So that's why you take it as it is equal to 100. Okay, so you can add this particular thing. How much you are getting? 5, 7, 9. So here 4 plus 4, 8, 8, 10, 11, 119. So for that pass, we are getting the value more than 100. We are fixing the upper bound to 100. Okay, so when upper bound is 100, so first you take weight is equal to 4 and value is equal to 40. Okay, so weight is equal to 4 and value is equal to 40. So if that goes, what will be the upper bound? Next, with 1, and this one is without 1. So if we go with the particular thing with 1, so this is item number 1, this is without item number 1. So if it is with item number 1, you take it as 100 minus 40. So it's 100 minus for 40. So you are taking the upper bound as 76 without 1. So that is 100 minus 40, you will get it as 60. So now you come for the with 2, without 2. So if you are going with 2, okay, so with 2, the what is the weight you are getting? 4 plus 7. So 4 plus 7 is equal to 11. So without 2, so without 2, how much you are getting? So without 2, so weight is 4, value is 40. Weight is 4, value is 40. The upper bound is equal to 40. So if it is 11, so is it feasible? So weight is 11. What is the maximum capacity you can have? It is 10. So as 11, it is greater than our knapsack capacity W. So this cannot be feasible. So come for this part. So for under 4, without 2, you are getting it as value W equals 4. Without 2, you get W is equal to 4, V is equal to 40, the same thing. So upper bound is equal to 70. So now you compare with 3, without 3. So with 3. So if you are going for with 3, so here you are without 2. So without 2, so leave this 2 part. So 5 with 3, that is 5. So 5 and 25. So with 3, you are getting 5 plus 4 is equal to 9. 40 plus 25 is equal to 65. So what is the upper bound you are getting? Upper bound is equal to 69. Okay. So that is the upper bound value you are getting. So without 3. So without 3, it is only you are having only 1. So that is W is equal to 4, V is equal to 40, UB is equal to 64. So inferior to node 8. Okay. So now you come for this particular thing. So finally, upper bound is equal to 69. So now you go with 4 and without 4. So with 4. So with 4, what is the W value you are having? So it is 4 plus 5 plus 3. So 4 plus 5 is 9, 9 plus 3 is 12. So will the W is equal to 12 is feasible? As our capacity is W is 10, we can't fix this particular 12 value. So that's why we tell this one as not feasible. So come for this one. So without 4. So without 4 means, so you are going with 4 as well as 5. You didn't place 7 also because it is not feasible here. With 2, it is not feasible. So 4 plus 5 is 9. And what is the value? 40 plus 25 is 65. Value is equal to 65. This is the optimal solution what we are having. So because what are all the things we have taken? So 1 you have taken, 2 you have not taken, but you have taken 3 and 4. So out of 4, how much is feasible? 1 is feasible, 3 is feasible, 1 and 3. So 2 and 4 you removed. So 4 plus 5, that is 9. 9 is the optimal solution what we have given. So that's why you have written W is equal to 9, V is equal to 40 plus 25 is equal to 65. Value is equal to 65. This is the optimal solution what we found for the branch and bound. Okay, so discussion. Solving the knapsack problem by branch and bound has rather unusual characteristics. For the knapsack problem, every node of tree represents the subset and also a feasible solution of the items given. We can use this fact to update the information about best subset seen so far after generating each new node in the tree. If we had done this for the instance investigated above, we could have terminated nodes 2 and 6 before node 8 was generated because both are inferior to subset value 65 of node 5. Okay, so that is up to traveling branch and bound traveling salesman problem as well as 0 bar 1 knapsack problem. So that we shall see that we have seen here. So till now we have gone with a in today's class, we have discussed a traveling salesman problem and also the 0 bar 1 knapsack problem till you have to go with a list branch and bound solution as well as FIFO branch and bound solution. So for that, these are all the concepts of branch and bound you are having. So that we shall see in the next upcoming classes. So that is up to understand this particular concept. I will explain it again. So initially you will be having W is equal to 0 and V equals 0 with the upper bound value. Upper bound value we can take it as 100 because how this see the value of the upper bound, it is 40, 42, 25 and 12. In adding all these values, it will be greater than 100. So that's why we reach the upper bound to 100. Now you have to go with one, without one. So with one, what is the value of item one? Where W is equal to 4, V is equal to 40. So 40 plus 4. So that's why we have written W equals 4, V equals 40, upper bound is equal to 76. So what is the upper bound you are finding? It is 76. So without one. So without one, no values of W and V, upper bound is equal to 60. So now inferior to node 8, you leave this particular because upper bound is 60. So here any value is you are having greater than 60? No. So come for this part. So inferior to node 8. So all these values are less than 60. Upper bound than 60, no values you are having. So you can't continue without one. Go with one. So under one you are having with 2, without 2. So with 2, 7 plus 4 is equal to 11. You can't. So without 2, you will be getting 4. Okay, so this is node 2. Node without 2, that is W equals 4, V equals 40, upper bound is equal to 70. Now you come with this part. Here it is not feasible because our capacity is because our capacity is 10, but here W value is 11. So not feasible. So go with without 2. So you are having W equals 4. Yes, it is feasible to our location. Now you choose with 3 and without 3. So with 3, 2 you have not taken. So with 3, that is 4 plus 5 is equal to 9 and its value 40 plus 25 is equal to 65. Its value is 69. So without 3, so W equals 4, V equals 40, upper bound is equal to 64. So as you all, any value is greater than 64? No. So any value is equal to 69? So now you go with 4 without 4. So this is with 4, you will be getting it as 4 plus 5 plus 3. So 4 plus 5 plus 3 is equal to 12. So it is not feasible. This one you get without 4, W equals 9. So that is 4 plus 5 is equal to 9. And 40 plus 25 is equal to 65. The value is equal to 65. So that's why you take it as optimal. Okay. So this is up to state space tree branch and bound algorithm for the instance of the knapsack problem. So this we have seen for every node represents a subset and there is a feasible solution of items given. We can use this fact to update the information about the best subset seen so far. If we have done this for the instance investigated, we could have terminated nodes 2 and 6 before it was generated. Okay. So have you understood? So, so this is the main headlines. So in today's class, we have discussed about a traveling salesman problem using branch and bound, as well as 0 bar 1 knapsack problem. Okay. So this is up to today's class. So in next class, we shall go with a LC branch and bound as well as FIFO branch and bound solution. So kindly go through this YouTube channels 1 DPMK. So understand the concepts. Okay. So kindly like, share, and subscribe for the channel and comment for any doubts you are having. So here I will be ending this particular session. So thank you all. Stay home. Stay safe. So thank you.